Okay, so for this lecture, we'll talk about game engine architecture, and we'll bleed a little bit between both the architecture that you will do within your games and the kinds of architecture that you find within a game engine itself. What we mean by architecture when we talk about this is really the way you organize your code. So, if you haven't had much experience writing code yet, there are often many ways to do things, many ways to solve the problems, and opinions differ on how to do that, even in terms of what is a well architected system. So it's all subjective. However, there are some good practices to follow, especially as programming has developed over the last, say, 50, 60 years now, that lead us to what are some at least good practices, some tribal knowledge, some good things to do that seem to work well, even though in some cases there might not actually be like full research to back it up. So one of the key pieces that we have learned is that often, and this probably won't feel like the case with your code in class, but it becomes true very quickly after class, is that your code lives longer than you do and lives longer than you expect it to. So code you write today, you might actually be modifying in a year. And so the better you can write that code so that it is understandable, so that it is clear and clearly separated, and some of this goes back to when we talked about programming and the parallel of the butcher there too. But this is, you want to break it up such that people can understand it, people can digest it, and then they understand how the pieces fit together, because often the code becomes complex and it becomes hard to understand no matter how you look at it. And so being able to break it down means that you can start to understand pieces individually, and at least start to understand, say, the rendering piece or the physics piece. Not necessarily how they interplay with each other all the time, and so you still end up with bugs related to those kinds of things, but at least you can maybe understand a single piece as a whole, right, as its own unit. And so for your case, in one instance, it's worth understanding how you're going to construct your game to follow that kind of practice. But it's also worth understanding that the Unreal Engine developers and other game engine developers, Unity and so on, they're all kind of trying to tackle that same problem by building a game engine that's both powerful and understandable and learnable. And so it's kind of your job too to understand the architecture, understand how each piece works, and how especially your game is going to work with each piece. And so that's kind of our task throughout this semester, is to really understand all of the pieces and to hopefully get you moving in the direction of understanding the whole architecture so that you can start to build your games that are well architected within Unreal. This slide is sort of entertaining. The architecture we're referring to is game structure, but you can think of there are parallels to architecture in the real world, where we think of like building design and things like that. So often when you design buildings, there are utility spaces like bathrooms. There are thoroughfares, places where you're going to move between rooms. You can almost think of them as like communication channels, right? Going upstairs or downstairs or through hallways. There are the rooms themselves and the use case for the room. And so each of these is kind of an example of each of those three, right? So on the left we have the utility spaces, and a poorly designed utility space in this case. Not a urinal you'd want to use fully occupied, right? The stairs there have some issues in terms of the way communication is broken up in some sense. The design of the building gets in the way of efficiently moving up and down those stairs. And a similar kind of problem on the right, where we have a room which has a role to play, but it's somewhat violated by previous architecture and just not. You can almost think of it as a refactoring gone wrong. Refactoring in code is when you look at the code, you decide it needs to change, and you start working on the change, but you sort of leave pieces there. We also refer to it as vestigial limbs or vestigial code, right? We think of humans with tails as having a vestigial tail. It's not a tail that actually acts in any way, but you still have sort of the bone structure. And so this is similar kind of error that can happen. So if we consider the pieces of a game engine, right? And we are going to, in detail, we've left physics out of here, but we have sound and input and a file loader. You need to bring things off of disk. Renderer and AI, those two we will go into in excruciating detail. And there are, a couple different ways to look at a renderer. There are 3D objects, 2D objects. The AI can interact with the player. It needs to know about items and creatures and bullets. The sound system needs to understand about sounds. And then as these factors within, say, AI are trying to update, let's say the AI helps update the player and the bullets and the items, all of these things then need to go over to the 3D system, or maybe the 2D system if you're looking at an inventory system, in order to display themselves for the world to understand how they work. They also need to represent some sounds. You need the sounds to be tied to the 3D because you want to have it localized in space. The player needs to know about creatures so that they can interact or cause damage. We've already kind of talked about that sort of thing in previous lectures. Same thing with the creature. The player and the items need to interact with each other, so you have healing potions, but the player also has an inventory and does inventory management. We have input that goes to the player. We have almost everything needs to save out to disk or read from disk at times. And if you just do this piecemeal as I've shown you here, without really the thought in place, then what you wind up with is this kind of spaghetti situation. So we actually refer to it as spaghetti code when you have many communicating pieces all talking to each other, and there really hasn't been enough thought given to how to channel these things, right? So how to build the hallways and the flow of traffic, and to avoid having these kinds of inefficiencies, or the fact that these things might communicate at the same time or be in the same space. All of that can have an impact, and so this is hard to understand as a graphic, and yet the code is going to be much worse, right? Again, we sort of thought about this from the standpoint of, well, we understand we need these things, right? We need a player, we need items, but we didn't really understand, or we didn't think about how these things are going to interact with each other in order to build out the architecture. So we just thought, well, I'm going to need a bathroom, I'm going to need a bedroom, let's just start putting these things down on the ground without any real understanding of the space. So it leads to many problems, right? So by having probably one of the worst is unintended or unexpected behavior. Those are really bugs. So you think that you're fixing something, or you think that you are changing a piece within the renderer in some way, and yet there's some sort of strong connection with the renderer into the file loading system or into the way the items are using it. And so because you didn't really think about creating a very narrow and controlled channel into the 3D renderer, the items are taking advantage of some aspect, say a special function call you've got, or a parameter that you pass in to build your rendering. When you make a change to that because you need to adapt for some creature element, suddenly all of your item rendering is broken, just because of the fact that they're kind of sharing the same code, and yet the items are taking advantage of something. So this is the kind of problem that you run into often, and it seems that, and of course it's very frustrating, right? Because you are building in your creature code, and yet you kind of forgot, or it was somebody else wrote the piece where the items were involved, and it doesn't make sense that changing something about the way that you're interacting with the creature, the rendering of the creature, should interact with the items, and yet because they're all using the same space, then it's very easy for those kinds of events to occur. And so of course when you see those kinds of problems, one, it's worth making sure that every small change you make, say to your creature or to your items to your player, you go back and you test your game very carefully, right? You maybe don't need to play the whole thing, but you go back and you start playing around and making sure that things that you think should still be working are still working, because you never know. So that's kind of the main one, that you get these unintended consequences of your code, or especially if code changes. And again, when you first start writing the code, it's going to be straightforward. But once you start getting some complicated blueprints going, you will run into those kinds of things. Of course, with blueprints, as we've already seen, they are very hard to understand when they're complicated enough. Thankfully, we can start to break them out. You can look at the comment blocks as almost a way to start to architect things, to say, here's a whole region, here's a whole room that I want to define as a certain kind of behavior, and I'm only going to have a few different things coming through, a few different execution lines or data lines coming out of my block A going into block B. And if you're really good about constructing your pieces in a useful way, and we'll look at some of the ways that this is possible with inheritance and component systems, you can reuse the code. And by reusing the code, you do run the risk of increasing your unintended behavior, but you kind of, if you're very careful about it, that's actually a saving grace, because you kind of reduce the number of lines, right? So if we were to imagine, say, a reusable piece right here that kind of acted as a go-between with the renderer and all of these other pieces that need to talk to the renderer, then we might actually be able to have one channel from the renderer here, and we're kind of narrowing the gap, right? We're looking at the way the items and the creatures might talk to this in-between piece that helps simplify some of the interactions that we might have. So it's worth spending more time thinking about your architecture if you've run into these problems, maybe going back to the drawing board and figuring out if there's a way to reorganize your communication lines or your structural lines, rather than just finding a quick fix that then leads to, it's essentially the same as adding new lines here. Every time you add a new fix, you add a new line, you add a new interaction between one of these things. And the more you can share, the more you can reuse, the more you can think about the structure, the better. So when you are trying to understand or trying to design your game in general, these are the things to think about, right? So you want to think about, especially the maintainability and the usability. Performance is worth considering, and it's worth putting into your thought process, but it can, a lot of people, especially as they start learning programming, start to find the joy of optimization, and it is a treat. It's one of my favorite things to do in code. Unfortunately, you can do this a little aggressively. Optimization tends to be a confounding factor for readability and understandability of code. So you really want to focus on readability and understandability, and then use things like profiling and other tools to determine, and especially algorithmic optimization, which really has more to do with the kinds of blocks that you're connecting rather than the way you're connecting the blocks, right? Or how you might efficiently sort of move things around, move pieces of data around, which is sort of the really low-level optimization. So I kind of put, don't think of these as an order, think of these as 5 categories that are all things that architecture can help you with, and things you should be thinking about, because stability is probably maybe as high as maintainability and usability, right? Okay, so there are language constructs in all the languages we have available. We're already seeing some of that with blueprints, and we see that with C++, and we see that with C#. And encapsulation is this idea that we can isolate and control the variables, or really associate the variables and the data together as one piece of it, right? So the language, the functions that need to talk to the variables, the member variables, the member functions, the events in the case of blueprints, all know about the variables that are on their object. And it's actually not straightforward to get the variables on some other object, right? So having these sort of side effects where I could go and modify the damage on another character is not trivial, and so because it takes extra work, there's actually value there. So you kind of design in a way that controls communications in just that sense. So by virtue of having some variables be public and some variables be private, you actually control how outside functions can, and if you recall, we have the sort of I opened and closed option in blueprints. By controlling that, you can encapsulate the data that you intend for people to see, those channels outside, and the data that you don't intend for them to see. So the things that you want to use internally that make sense for whatever game kind of mechanic. So again, going back to say rendering versus the player. The render system needs to know things about, say, the frame buffer and offsets about the VSync, and really nobody outside the renderer needs to know about that. The only thing that, say, the player needs to know about rendering is where to position the player character and where to put the model in space, like what the triangles are, maybe some animation components to it. And so it doesn't need to know about all the things that the renderer has available, and so by encapsulating some of those parts, then we can hide complexity, right? We control the channels, we control the communication lanes to just those things that make sense that we want to have. And so you should be thinking about this with your gameplay too, right? So maybe you don't want to make the health accessible outside the player. Instead, maybe what you want to do is create a new event or a new function that allows somebody else to call to damage the player or to heal the player. And then by virtue of having it on a function that they can call rather than modifying the health directly, you know that there's only two possible ways that health could be modified. And so if the health is changing somewhat apparently randomly, you no longer have to go look at all the code to try to figure out who might be accessing the health variable anywhere within the code. Instead, you're looking at just the two functions that modify the health on that particular character or on that particular blueprint. So that's maybe an example of starting to control these lines. So the next one that we see quite a bit with Unreal in particular is inheritance. We've already started talking about this quite a bit as we've looked at the Unreal system with the actor and character and pawn, and the fact that every blueprint that you create to some degree is going to inherit either from an actor or a character or a pawn. And by virtue of that, it will have some of those abilities. And so the way that we think about inheritance, especially if this is relatively new to you, is that we have a base class, something like an enemy, which is in some sense the broadest definition of the kind of thing that we're dealing with, right? So enemy is maybe, in this case, we'll call that the broadest one. We might even say human, right? So the human is our broadest category, and enemy is the next simplest. We usually don't start at the most general, right? It's kind of like when you start telling a story, you don't say, well, I was born and then I was raised. You start at a reasonable starting point for a story. In the same way, you start in a reasonable starting point for your inheritance. You start with something like an enemy, and then you decide, well, boss is kind of a special case enemy, or super duper boss is the really special case, like that's the end battle. But they can borrow features from each other, right? So all of the enemies, all of the little minions and so on that you fight, all inherit from enemy. Boss inherits from enemy, but it adds a little something special, right? So the boss would not only have hit points and the ability to attack the player, but also have special moves. And the super duper boss might be able to actually create new minions to fight the player in this case. So you start with sort of the simplest and the most general case, and then you get more specific as you inherit, and you add new capabilities to it. So we can also draw that this way, right? So we look at the base class and we say, my base class is enemy, and all of my children are more specific, right? So we have a specific type of enemy, a goblin, or another specific type of enemy, a dragon. And then we have an even more specific goblin, a heavy goblin versus a light goblin, and an ancient dragon. The other terminology we use is what's known as parent class. So we have children, which are the more specific ones, and parents, which are the less specific ones. It's always upwards. So dragon is a parent of ancient dragon, and enemy is a grandparent, or enemy is also a parent of ancient dragon. Usually people don't get too precise with that. And often, in some cases, you will also see a base class, base and parent used interchangeably. Sometimes base means specifically the top level or the root of the inheritance. And that terminology can shift, but the general idea is the same, right? That child is almost always the case, and parent or base might be depending on which language you're using. Okay, so the alternative to inheritance, or maybe in addition to inheritance, is what we refer to as a component-based system. And we also see some of that, right? So we were already looking at that with our blueprints where, we create, say, our cube blueprint, and yet we also add a static mesh component to it, right? And so the cube blueprint is, at the base level, just an actor. It can live somewhere in the world. We know that it can be placed in the scene to some degree, except that actually the static mesh component is the part that controls where it gets placed in the world, and the fact that it has a rotation. The static mesh component for a cube is the piece that controls all the information that needs to go into the renderer to say how to render this cube, right? What is its position and rotation in the world, and what is what are the triangles and vertices that make up this cube that we need to render. So we do define a class still like actor and character, which have some specialization, but then we can add and remove components to these things in order to get and define new behaviors or new functionalities to capture additional behaviors that we want to have. So it does add some challenge, right? So we will see this as we start to try to talk to the other actors. Sometimes we will get the actor reference, sometimes we'll get the component reference, sometimes we'll need to get the subcomponent within the actor, sometimes even in our own use case we now have to access a subcomponent. But this all leads to more encapsulation and more reuse. So component-based systems are especially useful for reuse if you do the encapsulation right. So if we come back to our example here, we see our some inheritance, right? So maybe we do have an enemy that has a goblin inherited and a dragon inherited. Again, you maybe think of the enemy as an actor now, and we're inheriting a goblin as one blueprint and a dragon as another blueprint. And then we can have a component definition that says, well, this is going to be a heavy goblin, or an ancient goblin, or a light goblin. And so the notion of ancient or the notion of heavy are components that we define certain capabilities around them. I'm not going to go try to come up with a concept as to why. Maybe it's armor, maybe it's health or something, or a way it changes health. But the idea is that if you've got this property for heaviness, you could add that heavy to the dragon, right? So you could say, actually, this is a heavy dragon. So we've got a heavy goblin and a heavy dragon. Or we have an ancient goblin and an ancient dragon. You could even consider having a heavy ancient goblin or a light ancient goblin, right? Now maybe a heavy light goblin doesn't make any sense, depending on your component definition. But this is where we get to the idea of reuse. This is less about the sort of communication control. In fact, it makes the communication a little bit more difficult, as we just talked about. But we do get to define small reusable pieces that we can say, well, I understand this concept of heavy. I've encapsulated all of the things that I need to understand about a heavy modifier. And now I can move that around, and I can even combine these things potentially. If I'm very careful about the design, I can modify and say heavy and ancient can actually be combined together. And if I add those together, I don't now need to have a very complicated hierarchy. I don't have to come up with a heavy ancient dragon, and does it inherit from dragon, or does it inherit from ancient dragon, or does heavy inherit from dragon? I just add these components to dragon, and I get different combinatorics out of it that create new and interesting entities. So both of these have their value, and it really depends on what you're doing, and it all comes back to, what are your goals, right? What are you trying to answer? How do you put these together? And it requires some thought, because each game is going to be different. We will look at some of these, we will see examples of this as we start to move through Unreal and start to use our FPS, but be asking yourself why say Unreal has broken things out the way they have, and how can you reuse that to make your game easier to work with? How can you define your items, or how can you define your bullets, or how can you define your puzzles or your world events in certain ways to take advantage of that? And we'll ask those questions as we move through the assignments in this class. Okay, so a common pattern that we run into with game engines especially is this notion of a singleton. You have probably seen this in programming classes if you've taken several. If you haven't, that's okay. Singleton is sometimes frowned upon in the computer science world because it is sort of a slightly better protected global variable, right? And global variables are often very bad because global variables lead you to the kinds of unexpected, unintended consequences that we talked about in the beginning, right? So a truly global variable means that any system, any of the blocks of our design, right? So any of these guys here can talk to a global variable that's been defined. So if the renderer has a global that says, here's my frame buffer, right? I've defined my frame buffer as global. Everybody, in order to render, all you need to do is just write some pixels into the frame buffer. So everybody's writing the pixels in the frame buffer. This is very bad because we don't know how people are modifying it. Or a simpler example we talked about is, if my health is public to everybody, then anybody, the creature, the items, the bullets, all of them, can just go in and directly modify the health. And the only way to try to understand who and how the health is being modified is to look at every single piece of code and understand who is doing it and try to put commentary and control to figure out when and how those things are happening. right? Which is not a great place to be. So this is the downside of the singleton. However, it turns out that there are a lot of systems in games that just lend themselves. So we do have a file loader, and we do have a renderer, and sound and input. And so in cases like that, because we have these kinds of large single systems that control a whole lot of things and a lot of people need to talk to, that's where a singleton comes in. So we would actually define our renderer as a singleton. We would define our AI management layer as a singleton, our physics layer as a singleton, the file loader, the input system. All of these things, and this is the case in Unreal, that all of these things really do present as singletons. Maybe not necessarily, obviously, but there really is only one defined in the entire game, one file loader, one input system, and so we can go and talk to it. So there are some downsides, but it does end up being a fairly common pattern in games, because we do actually have a lot of systems where we have the one system, right? So often there's also, say, a campaign manager, or an adventure manager, or quest manager, or even just a game state manager that says how far have you progressed in the game, and it's just keeping track of the quests you've completed and things like that, right? To say how far you are along and when the game is complete. So that itself might also be a manager of some kind, or a system. So we've already seen this pattern show up, and this is another one that this is in some sense the go-between that I mentioned before, that helps you control channels. So the idea of publish, subscribe, or producer, consumer, or observer, callback, which are all sort of the same thing, slightly different variations. What we have is that, well, let's take a look at the input system as we've seen it so far. So we have in blueprints seen that we can press the left or right button, or the up or down buttons, the W and S, or A and D. It turns out that the input system is also set up to receive joystick events. And so we could have to go in and define our events in such a way that we need to process both joysticks and keyboard events, and technically we actually do, because there are some slight variations there. But in some contexts we sort of don't. There's some ways to work around that. But you can think of it as, we don't necessarily care who's telling us to move right or left, or how they're figuring it out. We just want to know that there was a left command pressed. So we define our event as the axis event that's coming in, or the jump event, right? We don't necessarily care that it was a joystick button that was pressed, like the A button on our Xbox controller that was pressed, or the space bar. We just care that it was a jump event. And so on the one hand, we have the publisher say, well, I'm a joystick, and when the A button is pressed, I'm going to publish the jump event. And then on the receiver side, or the subscriber or consumer, we say, well, I want to know about jump events, because when the jump event happens, I'm going to cause my character to play this animation or this montage, and then I'm going to move him up in space by a certain velocity, and then he's going to come back down. And so we've separated the logistics of how the jump event occurs from the mechanics of what the jump event does. And so this is the kind of thing that helps us to start breaking down these lanes into, we sort of create a many in and many out kind of situation, where we can have many of these arrows going into our publish sort of situation, right? Again, think of a keyboard sending events, and a joystick sending events, and maybe even a VR system sending events. But then the event that's coming out on the other end just looks the same regardless of where the source came from. And so this is a great one, and you can do the same thing. You can define your own events in Unreal, and we will look at this especially with like damage and things like that, where you can actually say, I am spawning a damage event on you, and then I want you to respond to that damage event, right? So because I'm shooting you, or because my bullet hit you, my bullet's going to create the damage event on you when the collision happens. And so this is a different way to actually control that kind of thing, and to at least isolate, to say when we are getting into that situation where we want to know who's damaging us. We have only one damage event, and so we know we might not be able to easily understand who published the cause damage event, but we do know that the only way that damage can happen is through that damage event happening. So again, there are some downsides to this. There are the cases where when you get enough interactions, especially enough people that can potentially provide publishing events, right? Different pieces go. I say people, but it really means code here. That provides these different opportunities to publish, or multiple subscribers that are trying to do it, then it can become difficult to trace again. But if you've got just a few producers and a few consumers for each event pattern or each event pair, that can be a really great way to sort of isolate some of these things. Okay, so moving on from architecture, let's talk about a game engine. So it's hard to say when the first game engines came about, probably shortly after the first game was made. Quite a few games, especially in the earlier periods of the 70s and the 80s, really were just one-off games, right? It was also an individual developer quite often that was making it all by him or herself. And they would build all the code from scratch every time. But along comes the pattern, and of course every programmer worth their salt kind of sees a pattern and says, I want to figure out how to make a component or a reusable piece out of that, right? So as soon as you've seen something twice or two or three times, it's worth trying to figure out how can you make that reusable, rather than having to write it the third time, because everyone wants to always figure out how to automate their lives, right, and make it simpler. And programmers are the worst case for that. So early on with, say, Sierra games and probably several platformer games, and I imagine many of the Nintendo games, Mario and so on, there probably was a lot of capability there. One of the big ones that came about around the 90s, mid-90s, was the Doom engine or the Quake engine. And a lot of games ended up reusing those parts to essentially not just make Doom again, but actually make their own game with like this first-person capability, or the whole idea of a first-person shooter, but with a completely different skin to it. And so by creating this system where you not just have maybe an editor that lets you make first-person shooters, but it actually lets you abstractly define a renderer or a physics system or even a gameplay system in total, along with sound and input. All of these reusable components, you suddenly are able to make a lot more games. And so it's actually a fairly modern, within the last decade or so, that game engines are as fully capable as they are to, especially Unity's kind of the forefront of this, and Unreal is pushed along. So it's possible to make not FPS games in Unreal, though the very first Unreal, I think you could only make an FPS game. Unity's really pushed forward the idea that you can make almost anything in Unity. But in either case, it is now possible that you can create mobile games, you can create platformers, you can create 2D or 3D games, all with the same engine, and just reusing different pieces of the engine. And so the important piece is that the engine is defined and abstracted away down to what are the core elements that every game needs, right? And truly, what does every game need now with these engines? Because they want to make every game possible. And so they do the encapsulation and the inheritance, and they say, here are the reusable components that we think you will need to make your game. And so your job then is to learn what those components are, so that you can put them together in your game. So if we look at the basic structure of a game engine, and maybe this is in my mind why the term engine is used. There are probably different opinions every time. I think of an engine in a car as the thing that spins, that you can connect wheels to, and you can even connect your battery to, and you can connect a whole lot of things to, that kind of makes it all operate. But the core function of an engine is to have a spinning gear on the end of it, right? It's just it's a motor that spins at a faster or slower rate depending on how far you're pushing the gas pedal down. In fact, it doesn't even control the slowing down part, right? That has to be on the brakes, which stop the wheels and all that. And so the engine is like a loop, right? And so that's this kind of loop here is, or this spinning feature of an engine is why I think of a game engine that way, right? The fact that we're going to read the player input, and we're going to do the logic update, and we're going to do a render, and then we're going to go back to the start, and we're going to do that all again, and then we're going to go back to the start, and we're going to do that all again. It's the idea that there's this loop that just keeps going, right? We start the engine, and it starts running, and then at some point we turn the engine off, and then it's all done again. But in the meantime, it's running, and it's running at whatever rate it can run, whatever speed we can cause it to go, and it's doing all these things, right? At a very simple level, it's reading the input, running, modifying the game based on that input, and then rendering what happened as a result. So that's kind of the very basic version of a game. So I mentioned that it's going to run as fast as it possibly can, and there's some interesting things that result out of that. And this is sort of the first place that you need to start worrying about delta time to begin with. All right. So most game engines don't operate on maybe a regular tick basis. Instead, they will work as quickly as possible. So there are some game engines out there that actually do operate in ticks, and it used to be based on the hardware you were running on, say like a Nintendo console, that you could actually deterministically decide that I'm going to run my game at 60 hertz, right? Exactly 60 hertz, which is also known as frames per second, or 60 FPS. And then your tick rate would be exactly 1/60th of a second. And so you could really do all of your updates at a tick, and you could count ticks, and you can make assumptions about moving forward. The problem is that in modern systems, it's now we don't know how long it's going to take, and we don't necessarily care. And you'll see that your frame rate jumps from 200 to 80 to 30 to 20 sometimes. And so we have a variable frame rate usually, unless you're very careful about constructing things, because the hardware can support it, and we don't necessarily care to try to hit exact TV screens or all the things that we had sort of in the older days with some of the stuff. And so now, because of that, if you're to go in and just run and say, I'm going to move 5 pixels per update, and actually it's funny because if you play really old games, you'll see this kind of problem. They were running on and knowing that they had a 30 hertz tick, and so they did all their updates as, I'm going to move 5 pixels. So for instance, here's 5 pixels moving at 10 frames per second, and then here's 5 pixels moving at 50 frames per second. And so the problem is, you get a game that worked at whatever rate, maybe this was the rate you wanted to work. So an old game running at this is this sphere is a good speed, right, for that game. And then you run it in a newer system, and suddenly the entire game plays out in a few seconds. And this is entirely true if you try to go back and find games that ran in the 80s, and so they've actually had to do interesting tricks with the emulators to force the emulators to just run at a fixed update rate within the system and things like that. So for you, we've already seen delta time and world delta seconds. You need to keep that in mind with your updates, right? So you can no longer say, I'm going to move at a fixed distance because I can assume an update. Instead, you need to think about everything you're doing in terms of, say, speed, right? Or you need to determine whether or not it is a frame-dependent feature or not. Is it time-dependent? So if you are talking about something that is moving at, say, 5 pixels per second, you need to understand that you are moving it per second, and you need to multiply by world delta time in order to figure out how many pixels that really is, right? So you need to understand that sometimes your frame will be 0.1 seconds, and sometimes it'll be 0.02 seconds, and so on. So this is your first iteration of this. We will come back to that because delta time continues to haunt us throughout game development. So I've already kind of mentioned this, but let's go over it again just to make sure it's absolutely clear. In order to correct for delta time, you don't pick a fixed distance, you pick a speed. You say, I want to move at a certain rate, distance over time. So it could be 50 pixels per second, it could be in Unreal it's centimeters per second, in Unity it would be meters per second. And you use that time and you say, this is what that number represents. Unfortunately, you can't put meters per second or pixels per second or any of that on your variables. We've already seen, unless you put it in the name, and that's perfectly fine. You could say speed per second or speed _ meters per second is the actual name of my variable, which might not be a bad idea, but often you're just going to create your variable and say it's a speed, and then I also have this other vector that's a direction. So we certainly have types on our variables, but it's really only a floating point value, and it's not a domain or a dimensional value that says it's a meters or a seconds or whatever. But if you're aware of that and you're careful with it, then you know that you can do what's known as dimensional analysis. You can actually say, well, if I'm taking pixels per second and I'm multiplying by seconds, I'm sort of canceling out the seconds, and I'm just getting pixels. Or in other words, if I take a rate or a speed and I multiply by time, I get the distance, right? But it's not always distance. It could be the amount of work, right? So if I'm a pizza maker and I can make 25 pizzas per hour, and I do it for 20 minutes, then I know I've made around 8 pizzas, right? Or whatever it is. I probably did the math wrong. But you get the idea that it doesn't necessarily mean distance, but it does mean sort of an amount of work that is completed over time, given the multiply by time. So it works for many of those cases. So again, think of it in all of those. If you do have a game where you say have a pizza maker who's making pizzas, because that's the kind of game you want to make, or like a cook serve delicious kind of thing, then it's no longer movement, but you still need to be controlled by delta time in order to understand during this update how much of the pizza was completed, or how many pizzas were completed, if it could be completed in say 0.01 seconds. And then remember that your delta time is almost never fixed. There are some ways that you can sort of force that to happen with some special controls and special optimization and other things, but it's often, even with the controls, there's still a little bit of movement in the delta time. So it's worth never assuming that you have a fixed delta time and that you can just jump straight to distance. You always kind of want to understand the per time element and then multiply by your delta time. So here's again another version where now we are correcting, or this is, I guess, the correct labeling. So we're not like correcting the speed, but what we're looking at is seeing that here, because we move 5 pixels in 10 hertz, we're moving at 50 pixels per second, and this one actually translates to 250 pixels per second. So one last iteration is just to show you that by just using a fixed time and not considering our delta time at all, then it suddenly turns out that our game either runs faster or slower, right? Our actual speeds are much different. And the place where this will bite you is that when you first start using Unreal, your FPS will always be in the thousands of hertz, right? So your seconds here will be 0.01 or hundreds to thousands, right? Because you don't really have anything on the screen, you're not doing any actual work with Unreal. Your loop through the engine is very quick because there's nothing there. And so if you set all your gameplay with these very simple structures and very early on, my players should move it at 200 because 200 seems to be really good. Well, as soon as you add a bunch of stuff, suddenly you're in this slow space where your player suddenly moves really slow because there's so much more on the screen. And of course you don't want that. So let's look at a bit more detail about the game loop. So previously I showed you, again, this is sort of why our delta time changes so much. There are a lot of things that happen within a single loop. We will pull the input, but the actual logic update also involves AI, involves physics, maybe realistic physics, right? We do have that available to us, and we'll look at that. We have to go through all of our blueprints, all of our actors, all of our subcomponents on those actors, and figure out, did they have any tick events, or did the events fire during this round, and do we need to operate on some things? So all of our input events are probably firing every tick anyway. And then due to that is their animation that happens. So not only are we moving things around in the world, but we're actually animating them and running them through animation sequences, potentially either skeletal animation or blend shapes or vertex animation. And so not just that, but then we have to send all of that over to the renderer and get it to render a single frame, and all of this has to happen within hopefully 30 hertz at the least, and maybe even faster, 1/30th of a second. So a lot of stuff happening very, very quickly. So this list is also a pretty good summarization of what we're going to look at in terms of the engine components this semester. So let's kind of go through them and summarize a little bit. And the first one is the input system. So we won't really go in depth on what an input system does. A lot of the work is actually handled by the operating system. But it does do a lot of work in terms of being able to capture the many kinds of input that we might actually have coming from a system, and so Unreal can help us take care of that. A lot of work has gone into operating systems making universal USB readers work and things like that. And maybe one of the most interesting questions that comes out of the way you talk to the driver in the operating system is whether you're going to do buffered reads or direct reads. And game engines really do direct reads because we want to know what the current state of any button is and whether or not it was just pressed or just released. All the events that we're kind of looking at in terms of how we use them. And the buffered input is built around kind of the original purpose of a computer, which was like to do word processing and spreadsheets and things like that. So it's really meant to capture all of your inputs, and if the computer gets behind, because it can in some cases, it'll keep track of all the keys you pressed and then give them all back to you. But we don't necessarily care about that. So if our frame rate is running lower, we don't really want to store up the fact that the player is hitting right a whole bunch of times or hitting the space bar to jump a whole bunch. We just want to know, are they doing it right now? This does mean that to capture input correctly, you can sometimes miss keys if your frame rate is not fast enough. And so this is one reason that we actually care about having a higher input rate for input reads, because people can actually press keys and expect their keys to be pressed at kind of a higher rate than 60 hertz. And we'll talk more about this, especially when we talk about AI. But humans are not really fast at reaction time, but they're faster at kind of anticipating and depending on when their inputs are going to actually be met with a response. So the other thing besides just doing the direct read to understand what the current state of the keyboard is also to handle input mapping, and that is what we've already started looking at with the input system, and we'll look at much more, is that we can actually have multiple sources of inputs. And this goes back to this whole notion of the publish subscribe thing, where we have multiple senders, and the fact that we can actually have a joystick sending in a jump button by pressing the A or the space bar doing that. And that's this whole player input mapping. And so we'll have a chance to look at that more in depth later, especially the way that Unreal is handling that for us. But that's kind of the big pieces of the input system. So then the AI is sort of another input system, especially in the way that the Unreal Engine handles it, and that is that AI ends up being kind of a player control. So a pawn can be possessed by either a player and have control taken that way, or by an AI, in which then it's actually being controlled by an artificial intelligence. And so if you're not familiar with artificial intelligence, that's the notion that we can have something that acts somewhat intelligently to respond to the player. We will certainly go into that in much more detail when we talk about it. But for now, you can understand that this is something that happens that kind of provides the antagonist, or in some cases an aid to the player, and really acts as another piece of gameplay, but it acts as sort of semi-intelligent, looks like another human, or at least another intelligent being in the game. And then physics does a lot of work that looks intelligent in some cases, but it's really kind of meant to be the world system at large, right? So, where the AI might provide gameplay in terms of providing us something of a challenge, an alternate human or what have you, the physics provides the challenge in terms of all the rest of the gameplay. And we'll talk about the fact that physics can be realistic, and often the systems now allow for that, and of course things like the fact that you can't move through walls, or that you bounce off of them, and then the friction that controls you. But they don't necessarily have to be fully realistic, and sometimes we don't really want that, because what we're making is a game and not necessarily a physics simulator. Part of the value of the physics system really is the fact that it kind of models the whole reality of the game. And so in a lot of ways the world at large, whether or not Mario can jump up and knock a block, is sort of the physics of the Mario world, even though it doesn't have any bearing on our world in particular. And then the main place of where we're going to live, of course, is in this actor, tick, and events, and the things that we're going to respond to. And so that's really this section is going to be throughout the semester. We're going to come back to this. You're going to do some implementing now, and you're going to do some implementing on the next project, and so on. But this is going to be a recurring thing, and this is where our code lives, and this is where we do a lot of the other gameplay logic that isn't necessarily the physics in the world, but really the other things, the pushing buttons to open doors, and having the right key and all that kind of fun stuff. And then animation takes care of, so we'll look at the fact that physics does a certain kind of animation, right? So as you're moving through a world, you are moving objects, but there's more to it than that, and there's more to the way that humans move and creatures move that isn't just a statue sliding across the floor. It's actually a human that's moving by moving their feet and legs and their arms swinging. And so that's where the animation system comes in. It actually moves all of the vertices. So we'll worry about the fact that we need to position the vertices somewhere in the world based on where the character is positioned, and how that's respective to the camera, and how it gets rendered to the camera, as we'll talk about in the next step. But we also need to worry about how the character's stepping and what pose they're in. And so the animation system takes care of all of those kinds of details for us, and works both with the animation controls and the way that we can specify how we're moving the character, make sure the feet aren't sliding on the floor, make sure the correct action is played at the correct time so that it looks like the hit was made in the right way, and all of that kind of interesting space for gameplay as well. But a lot of the animation, of course, is really about communicating to the player what's happening, either from the AI or from the your own player, just responding to the physics in the world. As you're sliding down a space, maybe you need an animation that captures that as well. So animation is really important as a communication tool to the player that they're really responding to, maybe even in some cases more so than how the rendering works. And then rendering is where we will cover how a triangle becomes a pixel, much like a bill becomes a law. And we will look at the process by which we specify our triangles, we pass them into the graphics card, they get transformed into the camera space, they get rasterized into pixels, and then even going further, take pixels and understand how lighting works to some degree, and how the materials work, and how really a material is more than just a color. It's a color plus kind of a physical response to light. And so we'll look at all of that as well, and how we do control all of that from within Unreal. And so this will wrap up a major portion of what we'll talk about this semester in many pieces as we go through. And so you can look at this as a guideline. It will not be in this order, of course. Really, the order is how these are being used by the engine. But the way we talk about them in the class, of course, will be in an order that maybe hopefully makes sense to you in terms of how you use it.